Today, we're going to dive into how quantum algorithms actually work, how they manage to find that one right answer in a giant sea of possibilities. And here's a spoiler. It's less about brute force and way more about a kind of beautifully orchestrated performance. And that quote, that really gets to the heart of it, doesn't it? We're not just talking about building faster computers. No way. We're talking about a completely different way of finding a signal in the noise. A method that taps into the very music of the universe itself. You know that feeling when you've lost your keys or your phone? That frantic sifting through all the wrong places, the same pockets, the same cushions. That's the problem we're talking about here, just on a cosmic scale. We're trying to find one single perfect note in a massive, deafening roar of wrong ones. But what if you didn't have to check every single possibility one by one? What if you had a kind of inner spotlight, a harmony that just guides you right to the answer? Now, it sounds like magic, for sure, but it isn't. It's actually the core principle behind something called quantum interference. Okay, but before we can really understand that harmony, we need to tune our instruments. And that means doing a quick recap of the three big ideas in quantum mechanics that make this whole performance possible. First up, we've got superposition. This lets our quantum bit, our qubit, be both a 0 and a 1 at the exact same time. Then there's entanglement, which links two qubits together so they instantly mirror each other, no matter how far apart they are. But the real star of our show today is interference. This is the secret sauce. It's how all those possibilities are forced to compete with each other until only the right answer is left shining. So let's think of this whole interference thing as, well, a dance, a performance. Imagine all the possible answers are out there on the dance floor, but through a very specific choreography, only the correct answer ends up in the spotlight at the end of the song. So, okay, what exactly is quantum interference in plain English? It's the process where all those potential outcomes can either reinforce each other and get stronger, or they can clash and completely cancel each other out. It's this beautiful, carefully controlled battle of probabilities. And this battle really has two key moves. On one side, you have constructive interference. This is where the waves for the correct answer all line up and get louder and louder and louder. And on the other side, you have destructive interference. This is where we deliberately make the waves for all the wrong answers crash into each other and go silent. It's how we mute the noise. And that's the whole point, really. Quantum computing isn't about brute force. It's all about finesse. It's about carefully, precisely tuning this quantum orchestra until all the wrong notes fade away, leaving just one voice, loud, clear, and absolutely unmistakable. So, how does this actually play out in a real algorithm? Let's get practical and look at a famous example that puts this whole idea to work. It's called Grover's algorithm. You can think of it as our quantum spotlight, designed to find one specific face in a ridiculously massive crowd. Okay, the power here is just absolutely incredible. Let's say you need to find one name in a phone book with 1 million entries. A classical computer would, on average, have to make 500,000 checks to find it. That's the huge bar you see here. But with Grover's algorithm, it only takes about 1,000 checks. We're talking about a bar so small you literally wouldn't even see it on this chart. It's a completely different leap. All right, let's actually visualize this. Let's say we have just 10 possibilities to search through. At the very beginning, thanks to superposition, every single option has an equal 10% chance of being the right answer. So the stage is set. But right now, the spotlight is just shining equally on everyone. But then we run just one round of interference, one single step of our quantum dance, and look what happens. Whoa, the probability of the correct answer just leaped up to 30%, while all the wrong answers, their probabilities have shrunk. The orchestra is already starting to tune itself. And then, after just a few more rounds, the music hits its crescendo. The right answer now has a massive 90% probability of being the one, while everything else is just faded away into background noise. And this is the whole trick. When we finally stop the music and take a measurement, we are almost guaranteed to see the answer we were looking for. But, and this is a big but, creating this kind of result requires incredible, mind-boggling precision. It really is a delicate harmony.
We have to understand not just how to write the music, but also how fragile the whole performance is.
And this, right here, perfectly captures the shift in thinking. Old school classical code is basically a to-do list. Do this, then do that, then do this other thing. It's rigid. But quantum code, it's more like a musical score. You don't command the answer, you just arrange the instruments, set the initial conditions, and then let the song of interference unfold on its own. Okay, let's bring this down to earth for a second to get a taste of this power in a way we can all understand. Imagine cracking a simple 4-digit PIN. You know, there are 10,000 possible combinations. Classically, you just have to slog through them, trying thousands of them on average. And with Grover's algorithm, 100. Just 100 steps. Not 5,000, 100. It's the square root of 10,000. It is an unbelievable speed up. And yeah, it's also a pretty stark warning sign for the future of digital security. Okay, but we have to be real here for a second. This quantum dance is incredibly, incredibly delicate. The tiniest disturbance from the outside world, a stray vibration, a tiny change in temperature, can destroy the interference and completely ruin the whole calculation. And it's not a silver bullet, it only works for very specific kinds of problems. So no, it's not going to speed up your trip to the grocery store. So as we bring all this together and hit our final chord, let's come back to that central beautiful idea, finding a secret harmony that's hiding inside a universe of noise. And, you know, maybe that's the real philosophy to take away from all this. It's not about forcing a result or pushing for an answer. It's about creating the right environment, setting up the perfect conditions, and then just trusting the process to let the correct outcome sing for itself. And that kind of leaves us with one last thought. This whole principle of amplifying what matters while silencing what doesn't, it feels deeply human, right? So the question isn't just for a quantum computer, it's for us. In a world with so much noise and endless possibilities, how can we interfere to tune our own lives and hear the one true note we're all looking for?